Hello, I'm Jan Horacek from the Institute of Plasma Physics in Czech Republic. I will speak to you about innovative concepts for extreme heat load tokamak divertor, which is a topic which I presented last week at the International Symposium on Fusion Nuclear Technology. I will speak about mitigation of ELMs, edge localized mode, by fast strike point sweeping, which I will try to convince you that achievable factor of surface temperature suppression is between 3 and 5, and it requires some non-trivial hardware on European demo reactor. Liquid lithium tin divertor may seem a bit more interesting, because it can survive steady and transient heat events by evaporating, which unfortunately cools down the plasma. Then I will try to motivate us that we need plasma facing components which can survive more than 10 megawatt per square meter, which is usually considered by most of the scientists that it's enough, but I think it's not enough. And then I'll try to tell you that we just performed conceptual experiment of plasma facing components surviving 60 megawatt per square meter. A fast divertor strike point sweeping is a novel technique which is necessary because, according to Thomas Eich model, which is in fact the parallel energy density which is inside ELM filaments, which is in fact pedestal pressure multiplied by the connection length, with respect to the experimental measured energy density on compass, new data on compass tokamak and mass tokamak here, and jet data from infrared cameras, and also novel data from divertor probes are shown here. They well fit inside this model, and the extrapolation towards ether yields as a value about 15 megajoule per square meter, which you project it perpendicular to the surface, you get to the value about 1 megajoule per square meter, which is already above the melting and cracking limit of tungsten. In other words, it gets to temperatures about 2,000–3,000 kelvins. And if we don't mitigate it anyhow. So this is of course a problem, and then we can multiply the known ELM mitigation techniques like resonant magnetic perturbations or impurity seeding by our new engineering concept, which is pretty simple from physics point of view. It means to fast sweep the strike point, spreading the power within the ELM or QC filaments, space and time scales. So the idea is to install dedicated coils inside the divertor area and put them into resonance circuit with a capacitor bank, and from time to time to charge this resonance circuit by a DC power supply, and each time just wait for one ELM, sweep for a few milliseconds, and then stop, and then wait for another ELM and sweep again. The geometry for European demo is considered as such, as the demo central team does it. It means that we need in every divertor cassettes, assuming there will be 54 such divertor cassettes, we need one outer and one inner target coil, which would be about 1 meter long and 30 centimeters wide. So it's about 80 kilos of copper, including 100 meters long cables coming to each coil. And such a coil needs to be installed between the blanket and the divertor cassette module, and which is about 30–40 centimeters above the strike point. So there is virtually no plasma, so that's why we believe there can be a hole inside the baffle. The hole would be between two divertor cassettes, so it would be shielded, magnetically shielded between each sector. So in a top view it would be like fish scale, so there is a possibility to have a hole like this, and it would need to be about 10 times 30 centimeters. It can be filled with some plasma facing component but non-conductive, and this could be somehow tricky because electrical insulation under huge neutron flux can be quite tricky, but we don't know much about this. Anyway, we assume that it's possible, and then such a coil would be built from 6 mm thick Litz conductor. Right, and then already in 2017, when we started this first time, we performed simulations by heat conduction, and we tried to decrease the surface temperature by a certain factor, surface temperature rise during the elm crash, and it's a this function of the sweeping frequency and amplitude, depending on also on the time scale and spatial scale of the elms themselves. So we developed such a scaling relationship, and assuming it could be possible. So then, assuming we need, let's say, 9 centimeters sweeping amplitude, we then simulate a special divertor coil. In fact, it's a solenoid which generates mostly polyidal magnetic field, which then penetrates through the X point to the second inner target coil, and then it goes through the alternating magnetic conductor back to the original coil. And we simulated this in 3 dimensions because the particles are flying in 3D. So we start their tracking from the midplane down to the divertor. It goes once or twice around the toroidal circumference. So it goes through approximately 50 to 100 such divertor cassettes. And then they are deviated, the magnetic field lines are deviated, and then they go to a slightly different position at the strike point. Unfortunately, there are 2 effects which decrease this amplitude of the sweeping. Decreases with sweeping frequency as such that taking into consideration the COMSOL eddy currents, it decreases exponentially, and also the effect of slow ions, because they have only 6 kilo electron volt temperature at the pedestal, so it takes a non-negligible time to penetrate through this perturbing field. So with a decay frequency of 2.5 kilohertz, we see that the amplitude decreases. In other words, the frequency must be below 2 kilohertz and way above hundreds of hertz, because otherwise it would be too slow. We took into account some vibrations, etc. So requirements for the fast sweeping is summarized in this paper from last year, published in Nature Scientific Reports, with my colleagues here mentioned, and the parameters are as such, assuming that 18 kilovolts can be applied on each coil because they have non-negligible inductance, and putting their reasonable transformer with 100 microfarad, we would get a factor 3.1, the suppression of the surface temperature rise during the elm crash, which we consider as quite interesting factor because it corresponds to decreasing of the energy. We just spread it on a larger area. Unfortunately, during this process inside a coil which weighs only 80 kilograms, including the 100 meters long cables, we would dissipate 0.2 megajoule in each coil, which in all the coils together, 54 of them, so which we consider quite reasonably low. If we want to increase this surface temperature suppression up to factor of 5, then unfortunately we would need much higher voltage, 120 kilovolts, which is probably would be very difficult, and even more difficult would be 2.2 megajoule being lost per every elm as a dissipation energy inside those coils, which is probably out of question because it's just too much. 22 megawatts would be for 10 hertz frequency. So this is, I would say, worth considering further for the EU Demo Central team for machine integration, whether it would be really feasible, or maybe it could be used on other tokamaks like STEP or SPARC or the Craft in China. And because in China, a team independently of us installed something very similar to what we presented already in 2017 in this paper, just a polyol coil which does the same thing, this strike point sweeping, and they really installed it. It's not only simulation. They swept it with up to 100 hertz, and with this, using infrared camera, they seen that the surface temperature really decreased during the sweep when the sweeping amplitude increased its amplitude. However, when the speed of the strike point changes the direction from positive to negative, then it crosses 0, and at this moment the surface temperature rises to nearly the same value as without the sweeping. So this is not really what one wants, and the main reason for this is that the Sweeping frequency is only 100 Hertz. It's not 1.3 kilohertz as is required according to my simulations. So this is something what should be considered and increased. However, with such a coil it's probably difficult because its inductance is probably too high. That's the main advantage of this geometry, that we use a solenoid instead of a one polyol coil. Right, so this is worth further consideration. And then another option is using liquid lithium tin divertors, which survive steady and transients. That's what we demonstrated already in 2019 and published in 2020 in these two papers, that liquid metal target which we put there in the outer strike point, inner strike point area, survive 12 up to 15 megajoule per megawatt per square meter, which is probably the world record in a tokamak, including ELMS in ELMI H mode. And it was using lithium tin alloy. With lithium we were not lucky because it oxidized and then it melted immediately the target, so it was not very useful, but it was because of oxidation. We tried especially to shape this target in such a way exactly in order to achieve very high perpendicular heat fluxes. We observed that there is some neutral cloud of 6 centimeters around the target, which corresponds to the neutral lithium, which is important for, I will tell you why in a moment. Then we also demonstrated survival of disruption, vertical displacement, even when the plasma fall down nearly on the target, and increase the surface temperature by 200 degrees within 200 microseconds, and there was no issue with this target. We could continue operation without any problem. We developed a model which we called heat LMD, liquid metal divertor, which in fact takes into account heat conduction inside the target, because it's a really slow, very fast process. So heat conduction is in fact the dominant process for reducing the surface temperature. It takes as input to the code the temperature, density, and so heat fluxes measured every microsecond and millimeter resolution by divertor probes. And as you can see, the correspondence with the infrared camera is very good, is excellent, including the ELMS which arrived on the target. We have like 100 ELMS during this one short discharge. Here you can see the spatial distribution of these temperatures. And there were, however, two mysteries. That once the strike point shifted away from the target area, the surface temperature did not decrease on the infrared camera. It continued well at the more or less the same temperature, whilst of course the simulation tells us that it must decrease because there's just no heat flux on it going. So this is quite a mystery why this could happen. And then there was also a mystery concerning ELMS, because they should, according to heat conduction equation, only the surface temperature should rise only by about 3 Kelvin instead of 30 Kelvin, which we really observe by infrared camera. This could be explained by surface thermal insulation of the capillary porous structure, which is interesting observation. Nobody ever reported this, and it's quite possible that it exists. Right, the vapor shielding regime was not reached in our case, even though it should be above already 700 degrees Celsius. And the reason is because there was very large mean free pass of the lithium neutrals ionization. It's about 6 centimeters. This value comes from the bit 1 simulation as well as the observation with visible camera. In other words, this cloud of neutrals was shielded not only the hotspot, which is about 6 millimeters, but 100 times larger area, a ball of cloud. So it was cooling the local area very small, so it was not really efficient. So if we made it toroidally symmetric, this target, then it would be very efficient and we would reach the vapor shielding regime. So we took this code with such inputs as shown here in this graph. We took some CPS heat conductivity from literature, and especially the lithium tin evaporation, sputtering, and radiative cooling. And then the input of the code is the surface temperatures compared with infrared cameras and with the visible camera, which is in good correspondence. So then we could take this interpretative code to make it predictive for compass upgrade tokamak, which is a new tokamak built in Czech Republic with 5 Tesla toroidal magnetic field and a major radius 0.9. So it will be the strongest tokamak magnetic field in operation once it will be built in a few years from now. And then we take some inputs to this code from rescaled divertor probes data, the same as from COMPASS. We rescale them according to heat flux scalings, and then Fiesta and METIS simulations. And then the output from this code is in fact the amount of vaporized and sputtered lithium and tin. And this is then taken as input to the CORDIF simulations and later on into Aero, SolPS and BIT1, but now to CORDIF. And this we already know from this relatively simple code, much simpler than SolPS, what will be approximately the undesired central plasma cooling and dilution. And unfortunately it's quite strong. This we already published 2 years ago. In fact, on those, the white numbers in white colors corresponds to what has been already published. And this is shown, in fact, that once we put there a target, we calculate certain amount of released, vaporized and sputtered lithium and tin. And it's so much that according to CORDIF, it yields too high core plasma dilution, 9%, and 1 megawatt of radiating power, or 5 megawatts even in the case of tin, and core concentration 10 to minus 3, which is way too much. It would means radiative collapse because 5 megawatt is more than the 2.5 megawatts input power in our medium power H mode, which we consider in this case 2.5 Tesla and 0.8 megaampere. On the left part, it's the geometry with this target. It means that the target would be at a high angle, like 45 degrees, very small hotspot, only a few square centimeters, and that's why it would reach heating of 160 megawatt per square meter. So huge power flux going on the target itself. So in this case, as you can see, the solution is not here. Here on the right side, we try to simulate the full toroidal divertor, which would be from this liquid lithium or tin. In this case, the area is 1,000 times larger, 100,000 square centimeters, but only 3 degrees. It means that the heat flux is only 60 megawatt per square meter. And in this case, again, we get radiative collapses because there's just so large area with not so much vapor and sputtering, but because the area is much larger, it's again not a solution. So in other words, in order to make it a functional target, we would need to make it thinner, not only using inertial heat sink into a thick piece of tungsten, but really putting there a cooling pipe 4 millimeters below the surface made of copper. And in this case, most of the energy is in fact transported away by the heat conduction inside the copper. In fact, 16 out of 16 megawatt, or half of this, is removed by heat conduction, and this already yields acceptably strong vaporization and sputtering because the surface temperature cools down. Most of the heat is lost by water. And in the case of this extremely high heat flux target, it's the same story. In fact, we need to extract 130 out of 160 megawatt per square meter, which in fact, maybe you know, it's not possible using any conventional water cooling systems because the limit is between 10 and 20 megawatt per square meter. So this is kind of science fiction from the water cooling power side. So what to do with this? Yeah. I will tell you in a moment. Firstly, before I'll try to explain you why we need to go to so high heat fluxes to demonstrate their feasibility. Okay, firstly, let's look at the baseline predictions for ITER. The heat flux which goes on the divertor target, the maximum one which can be sustained by the ITER-like cooling system is 10 megawatt per square meter forever, or 20 for short transients, like 10 seconds long short transients where the surface temperature cannot rise so rapidly that it gets below, it's still below 2000 degrees Celsius. However, the question is whether this is the prediction for future tokamaks. So for ITER, if you just take L mode, I took my own scaling and published in this paper 2020, assuming 30% radiation with zero fusion power, we already get to 10 megawatt per square meter. And this is because there is no turbulence spreading, there is also very few radiation. So when you take Q equals 10 scalable power of 100 megawatt, which is the which is the scenario which ITER wants to go to, in fact, then we know that the decay length would be about 0.5 millimeter, and then this means 200 megawatt per square meter if there is no radiation. So the radiation can decrease very strongly, this power flux, but in fact you need to decrease it really by a factor of 20. And this has been in fact achieved just 2 years ago, published by Matthias Bernen on ASDEX upgrade by the so-called X-point radiator mode, where really 95% of the energy has been radiated. But it was really the first time I have ever seen this in a tokamak in a controlled way. So hopefully these experiments can continue and demonstrate it's feasible for future tokamaks, because there are many considerations, requirements for such a X-point radiator mode. Another option, or combined with this, is the XGC1 simulations, which are consistent with experiments published in these two papers, which predict much higher decay lengths on future tokamaks. This is in fact shown in this graph, that the decay length decreases with the polaromagnetic field as such, and gets to a value about 0.5 millimeter for the polaromagnetic field expected on ITER. However, the simulation for ITER yields value which is 14 times higher. This is shown in this graph. This is the ratio between the code predicted lambda decay length and the Eich predicted from this empirical scaling, by factor of 14 higher. And this is only true for tokamak which has strong enough polaromagnetic field and large enough minor radius. In other words, it could be, it can be expressed as a b squared times major radius. In other words, the experimental verification of this new turbulence mode driven by ITG, ion temperature gradient, will be possible only at ITER itself, not before this device will be in operation, because no such large device and with so high magnetic field is planned in any future before ITER starts operation. So let's hope it will be true. Because we have many reasons to believe that it may not be true, and this is in fact shown in this graph. There are pessimistic turbulence and empirical predictions, which on the same graph we believe this XGC code is very tricky to verify, because as I said, experimentally it's not possible, and also from a theory point of view it's not possible, because there are turbulence codes which also predict the turbulence spreading, but the simulation for ITER would take 500 years for this code to run on 2000 simulator on 2000 computers, in fact, in parallel. In fact, so GBS code is not possible for ITER. However, GBS code has been found to have excellent match with compass data, just presented this week by Petr Mácha at EU-US Turbulence Workshop, in contrary to SOLPS, for example. And also 2 years ago, Maurizio Jacopin derived this scaling from analytical equations of the GBS code itself, which in fact, when I put there my data from 5 different tokamaks and scale them with this scaling, in fact I get very good match. In other words, this is a very good proof that this scaling can predict some reasonable values for ITER. And this scaling is in very good correspondence with these empirical scalings, which is also backed up by the heuristic drift-based model by Rob Goldstone. This is shown in this graph. This is the prediction by Rob, and this is the experimental measurements. And also scaling by Dan Brunner for just plasma pressure. Very simple scaling as a 1 over square root of plasma pressure decreases the power decay length to value of 1/4 for the SPARC tokamak and 0.5 millimeter for ITER at this parameter level. So there are these 4 different ways how to predict the future decay lengths are very consistent with each other, and they yield value which is order of magnitude smaller than the XGC1 code, in other order of magnitude larger heat fluxes. Such heat flux up to value 100 megawatt per square meter perpendicular to the surface has been already observed on Alcator CMOD, which is a machine without any fusion power. And these crazy numbers are in this way predicted for future tokamaks, assuming 0 radiation. It's really crazy numbers. So we don't know really what the future value will be, but I would say that new engineering solutions are probably really desired to go above 10 or 20 megawatt per square meter, which is really the engineering limit for today. So I have a good news for you that a water-cooled plasma facing component really can survive 60 megawatt per square meter. In fact, it really did. This you can see on this very quickly done experiments on air plasmatron, where we put the copper plate, which is cooled from backside by water. It has been immediately damaged on the left side. You can see it's melting really on left side, but the left side is really poorly cooled. It was weakly cooled on above and, or I would say strongly cooled above and below, and super strongly cooled at the center where the water flow was really going, because it was not really going on the edges. Why we believe that there was 60 megawatt per square meter, it comes from, in fact, a calibration of our target. We just put there, instead of the target, we put there a piece of graphite, which in fact heated up to nearly 4000 Celsius within half a second, and from the time and space evolution of the surface temperature, we could derive by COMSOL multiphysics 3D and heat conduction equations that the heat flux was really 60 megawatt per square meter on this area, with the same scale on this area. So we are now asking for a national project for systematic study of this technique, what are its really limits and how to increase them. So in our summary, I told you about unmitigated ether elms, that they need some better ways how to decrease their energy, and one of the options which can be combined with other RMPs and impurity seeding and so on is the fast strike point sweeping. And with 7 centimeters and 1 kilohertz, which requires 18 kilovolts voltage on specially dedicated copper coils in divertor area, we could decrease the surface temperature by factor of 3 on the European demo far future huge tokamak. And this has been published in these two papers. Then our Czech liquid metal divertor tokamak program started in 2017, where we designed an experiment which was then published in these 3 papers, where we demonstrated that a lithium tin plasma facing component based on capillary porous structure survived 12 up to 16 megawatt per square meter, including ELMS with 15 kilojoule per square meter. Major VDE disruption, plasma was unaffected, the target was unaffected, and however we didn't reach vapor shielding because our discharge is too short. Right, and we also observed that the lithium tin doesn't oxidize, which makes the operation pretty easy, and also it doesn't evaporate tin, only lithium, which is very good news for the tokamak. And then the same code which we used for this interpretation of the data, we used for predictions combined with other codes, and then we realized that for full toroidal experiment and also for target at a very large angle, we cannot really run it if we don't find some water cooling systems into the design, which is a complication. And if we really go to very high heat fluxes, then we have to assure that most of the heat flux is absorbed into water, which is beyond the limits of conventional water cooling systems, which is designed on ITER. And that's why we did an innovative water plasma facing concept which survives plasma jet at 60 megawatt per square meter, which we already demonstrated at technology readiness level number 3, and we want to continue with this, improve the technology readiness level, and that's what we are going further. So thank you for your attention, and I will be happy for any feedback. Jan Horacek from Prague.